Welcome to the Node Guardians podcast, where we discuss all things blockchain, decentralized web, smart contract programming, and cryptography. We're in good company today, as usual. I'm very honored to welcome Zac Williamson for this first episode of the third season of the Node Guardians podcast. Zac, it's really a pleasure to have you here. How are you?
Thank you very much. Yes, it's a pleasure to be here. I'm doing well. It's start of a new week, Monday morning in London, but I'm raring to go and mostly awake.
Is London sunny at this very moment?
Funnily enough, it is. Normally God curses these islands with terrible weather, but it's absolutely beautiful the last few days. So been enjoying my time outdoors. Perhaps a little more than I should be. I should be back indoors, underground coding and developing and designing. But that's
wonderful.
What it is. Cheers.
So this episode is going to be. Oh wait, actually, there's a bit of a mistake here. I'll just. This is hilarious. So I'm using StreamYard as a backend to record the episode, and this is live streamed to a French media. It's not supposed to be in English. I just scrolled on the wrong option when I started the recording. So I'll start the thing from scratch if you don't mind, and cut this. We have 40 people online here, so I'll just.
Bonjour.
Bonjour. Désolé.
Je m'appelle Zachary. Je travaille au Angleterre.
You know what? Actually, that'll make that episode more memorable than it is. I think we can just keep moving with this stream. It'll just be streams, but I'll be able to get the recording. So you know what?
Bien, d'accord.
In the crowd, I'll make it more interactive. So this episode was, I wanted to call it Anatomy of a Private Blockchain. So the idea is to break down and decipher and have you explain all the different components that make Aztec Network what it is today and where it's headed. But before starting this deep dive, we'd love to know more about you, how you ended up getting involved in the ZK space.
Sure. Yeah. So, wow. How did it all get started? 7 years ago, when I had a lot fewer lines on my face, I was a much smoother person back then. How did it all get started? So I'm a failed particle physicist by training. I wanted to unpick the mysteries and secrets of the universe, and then I realized that actually, wow, that's really hard. So I kind of crashed out of academia, became a programmer, a software engineer, because that's kind of what I enjoyed. And honestly, I fell into it because my friend, Tom Peacock, mutual friend of mine, was creating this technology startup involving blockchain. And he needed a technical co-founder. So my brother, who was really good friends with Tom, connected me with him. And yeah, we decided to work together. But that wasn't cryptography related. It was called Creditment. It was a syndicated loan platform for that used Ethereum, so TradFi on a blockchain basically. But as part of that product, we needed strong privacy guarantees, and at the time we didn't realize how difficult that was on a transparent ledger. But once we did, I started looking into zero-knowledge cryptography, things like how easy it would be to port the Zcash protocol to Ethereum, and the answer was very hard. But I basically fell down a cryptography rabbit hole. I found that I really loved the mathematics behind it, and because I kind of understood it a little bit because of my physics background, and it was intoxicating. This idea that you can combine this permissionless, decentralized, distributed ledger with this zero-knowledge cryptography, which allows that ledger to be encrypted, but people can still validate its correctness. So you can prove stuff about encrypted data. I can give you just random numbers, just it looks like garbage information but construct mathematical proofs that prove that this is an encryption of something, and that various logical statements can be applied to the unencrypted data. It felt like magic. So I kind of became obsessed with it, and that's how I became a cryptographer. And then I was fortunate enough to meet some very, very good influences on me. Jens Groth, the inventor of elliptic curve snarks, mentored me for a bit. I met Ariel Cabazon at a conference, and we started collaborating, and eventually that turned into Plonk, which was the landmark zero-knowledge cryptography protocol that enabled a lot of innovations in this space, that enabled us to pivot from being Creditment to being Aztec and who we are today.
So you're switching from one application to creating something that enables an arbitrary computation to run just a whole infrastructure for any logic to basically run. So something much more ambitious. That's the transition.
Yes. Yeah, exactly. So we were thinking, wow, we can build Creditments now, but it's so much more useful and important and valuable to create effectively an infrastructure layer that enables anybody to build privacy-preserving applications on a blockchain, basically enabling anyone to turn up and produce a Creditment. That was the original desire. Yeah.
All right, pretty cool. And now you are building Aztec Network, and you've been going through a few chapters before Aztec Network. We've had Aztec Connect, but what really interests us today is Aztec Network. Could you please define what the solution is at a high level, and then?
So it's a privacy-first layer 2 for Ethereum. So what we're trying to do is effectively recreate the smart contract ecosystem of Ethereum. This concept of programmable money, programmable assets, programmable identity, where anyone can turn up to the blockchain network, define their own currencies, their own rules around how to transact them, and interact permissionlessly with every other application or product deployed to the blockchain network to create these really diverse types of financial protocols or identity protocols or things like NFTs, whatever you want. What we want to do is recreate that ecosystem where you can have privacy as a first-class primitive. What that means is private state. So you can perform transactions without revealing who you are. You can prove certain permissions or credentials checks without revealing who you are, so that you possess a certain NFT, for example. For us, this is really the missing link that's required for privacy to really explode and hit the mainstream. Because the way things currently stand, you can't link meaningfully an identity with a cryptocurrency account, not without revealing to the entire world what you're doing and who you are. And that is extremely limiting for distributed ledger, where fundamentally what you're trying to do is describe ownership records of for things that have notional value. Not being able to tie that to a real world identity without leaking enormous amounts of information is punitively damaging and limits the potential use cases for a blockchain network. Even simple things like decentralized autonomous organizations, not being able to have private votes, for example, is extremely damaging, because there's a reason why in our democracies we don't have public ballots. It makes these communities susceptible to peer pressure. Basically, privacy is the missing link in our opinion, and so we want to enable that through the Aztec layer 2.
And one interesting thing to note here in the very case of Aztec is that it is a zero knowledge rollup, so it really has that privacy property that we do not find in other systems that are also called by the broader, let's say, crypto community, ZK rollups. They are actually validity rollups. Would you agree with the good old way of calling them?
Yeah, so I'm not going to beat that dead horse. I mean, ZK rollup, the name has been established already as this idea of using zero knowledge cryptography to create a rollup. But none of them are privacy preserving, not really, and it's very difficult for them to be privacy preserving, because when you're building a rollup like that, you've got to make some design choices very early on. So you have the choice basically between compatibility with Ethereum or some kind of base chain and privacy, because if you're trying to become compatible, so you could just deploy your smart contracts to a layer 2, then that means you're following the state model of Ethereum, which is basically an account-based database. So the idea is that on the Ethereum ledger, inside its state database is going to be an Ethereum account, and associated with that is going to be your Ethereum balance. So you could say, okay, well, we could use ZK to make this end-to-end encrypted, sure, but then if you then send a lot of cryptocurrency transactions, what's going to happen is these transactions are going to modify your encrypted balance, which means, people might not be able to see what's being, the values being changed, but they will be able to see a specific entry in the ledger is consistently changing. And so all it does is it means that instead of your identity being your Ethereum address, it becomes your encrypted Ethereum address, and nothing really changes from a privacy standpoint. You need to create a radically different kind of a blockchain architecture to enable strong privacy guarantees. So that's why we designed Aztec basically from scratch to do this. And it means that it's adding privacy to a ZK rollup is not just a simple matter of flipping a switch. It's a bit like trying to add privacy to Ethereum. It's taken us 6 years to do it so far. It's complicated.
So you have a different kind of account model that preserves privacy. I also imagine that when you're trying to communicate with the network itself, you're not interacting with your average RPC or node. You need to preserve the input so that it's not compromised by any operator in the system. And if you want to have client-side proving, you need to design some state-of-the-art cryptography, so domestic hardware will be able to make it work in a reasonable amount of time from Mr. Everyone's kind of hardware. I would love to dive deeper into this, but so Aztec is this general purpose private system that allows any an arbitrary smart contract to run. And I do remember your previous Twitter biography where you were saying that buzzwords are fun, and we hear about these ZK apps. I mean, these days we hear about ZK apps. Could you give us the behind the scenes of these zero knowledge applications? What do you do with the binary? What's going public? What's going private? What is a ZK app?
What is a ZK app? I think there's several projects that are trying to proliferate the phrase ZK app, and they're all using different definitions. So we don't use the phrase internally. We just say Aztec smart contracts. But I get what you're saying. Like, what would a privacy preserving application look like? Well, let's start with what does an Ethereum application look like? It's basically a bunch of Ethereum virtual machine bytecode embedded into the blockchain state database. So basically, you have this imaginary computer called the Ethereum virtual machine, where in the Ethereum yellow paper, its operations are strictly defined, so that it's very easy to program a simulator for this VM, which makes it deterministic. Given a certain program code and some inputs, you'll always get the same output. And that's not what a ZK app is, because if a user is sending a transaction to the Aztec network, that transaction doesn't contain instructions to execute code. It contains a proof of correctness that some code has already been executed correctly. So a ZK app is basically, so we have a programming language called Noir, which we use to write smart contracts. And a smart contract is split into a list of functions. And you can have public functions or private functions. Private functions modify encrypted state trees, state databases. So everything's hidden. The public functions are more like Ethereum, where you can modify a public state database. And what happens is that these functions each get compiled into zk-snark verification keys, and your contract is defined as the set of verification keys that make up all your functions. And so the idea is that inside the Aztec state database, there is you have a contract address, and associated with that contract address is a bunch of function signatures and verification keys. And a transaction is basically a proof of correctness. Well, part of a transaction is a proof of correctness, where the proof is associated with one of the verification keys that maps the function you're calling.
Oh, very cool, very cool. So that's how we could define it. And you've mentioned that Noirlang is the scripting language for these Aztec contracts. Could you tell us a little bit more about what led to the creation of a domain-specific language for Aztec?
Yeah, I can. So we have very unique requirements for what we need from a zero-knowledge proving system, because we have this focus on privacy, which means client-side proving. Effectively, if you're constructing a proof that contains a bunch of secrets, you don't want to delegate that proof to a third party that has a lot of computational resources, because that means you need to give them your secrets, which means that our proofs have to be constructed with relatively weak hardware. We can't solve our problems by just throwing more CPU cores, more servers at the issue, which meant that we wanted to have a language that can very maximally efficiently compile down to constraints. This is not so this is kind of in contrast to an approach like, say, RISC-0 SP1, where the idea is, okay, well, let's just take this existing machine language, RISC-V, that all computer programs compile down to, basically, and say, let's just evaluate RISC-V in a zk-snark circuit. Well, that works. It's pretty groundbreaking what they've achieved, to be honest. But it only works if you can delegate proving to very, very computationally well-resourced provers, because it's extremely hardware intensive. You can't do this kind of stuff on a phone. So we're like, okay, we need to make a domain-specific language. We didn't want to use the existing ones out there because, in our opinion, they were far too user-unfriendly. As in, you have languages like CIRCOM, but the issue with that is that you really need to understand circuits to write a CIRCOM program. The idea is, like, you're basically writing two programs in CIRCOM. You're writing a program that defines how to generate the inputs to your snark circuit, and then a program that defines how those input values are kind of constrained. And it's a weird mental model that's not intuitive to programmers. So we're like, no, we want programmers to write in a language that's very much like Rust, where what you see is what you get. It's intuitive and straightforward. You don't need to be a cryptographer. You don't need to understand circuits. And so that's why we thought we actually need to have relatively tight control over the language stack to make that a reality. So yeah, so that's why we started out with Noir.
Yeah, probably back in the days when you were designing this, even Cairo was an extremely low-level system. Like Cairo 0 was not the friendliest language at all until it got totally overhauled into something brand new that has a linear type and Rust-like syntax. So I can imagine the crazy effort of engineering that went into designing a language that is actually optimized for proof generation in a context where you have extremely limited resources. So Noir is that front end. It is that language that we can use, and it is like it's compatible with general Snark backends and a bunch of other things. So are there like some Noir compatible backends that are being built right now that are exciting?
Yeah, that's a very good thing to add. Noir is not like an Aztec specific platform that uses Aztec cryptography. We designed Noir to be completely agnostic to the underlying cryptography. What Noir does is it's a language front end like Rust or like C++, where it compiles down to something called like an intermediate representation. So a list of low-level operations that can then be converted into a snark circuit. But how that conversion is performed is not specified by Noir, which means you can plug in different backends. You can plug in the Brettenberg backend, which is one that we developed. There is a Halo 2 backend, but it's quite out of date and needs to be updated. I believe a NARC backend is currently under development. And yeah, I think we're kind of interested in if we can get a Plonky 3 backend. So there's lots of interesting works on the backend side there for sure.
It's super exciting, and I do believe that these provable languages can actually have use cases that span beyond the actual Aztec network.
Absolutely.
Can you tell us more about that?
Yeah, I like they can go beyond Web3 entirely, really. Like this idea of being able to prove something is true without revealing information, without revealing sensitive data, is extremely valuable in a lot of use cases. So one of the ones that's kind of becoming quite relevant today is machine learning. Basically, being able to prove, for example, like prove the output of facial recognition machine learning algorithm without revealing the inputs is extremely valuable, because that means you get to keep all of your sensitive information and your iris scans and things like that. Don't need to share that. Or being able to prove that an image or a video was recorded with authentic hardware and wasn't generated by an AI. That again is something where zero knowledge could be extremely useful. And in a more general sense, something I'm excited by is this concept of I guess one could call it trust infrastructure. So the idea is, if you have a Web2 application and you want to request information about a user from another Web2 application, right now that's not very easy to do unless those application vendors like expose APIs to make that happen, and they don't do that because competitive reasons. But what you can do is instead you can make the user construct proofs of knowledge, saying like, I made an API request to Facebook, I got my user account data, and like here's my friends list, for example, and you can prove that all trustlessly. That kind of concept of being able to basically extract information from data silos that where the owner of that silo doesn't want information to be extracted is extremely powerful. And I think we're going to be seeing a lot more of that in the near future.
All right. And I wanted to ask you if you could like break down the life cycle of a transaction on Aztec Network. So let's say I'm trying to interact with an arbitrary contract. What is actually happening that ensures that throughout all the steps, whatever I'm sending to the network doesn't get compromised? Could you cover like different?
Sure thing. So let's start with the transaction origin. So if you're calling your entry point is going to be, you're going to be calling a smart contract. Aztec uses account abstraction, so that entry point is going to be your smart contract that authorizes who you are. But that contract is going to call other contracts, which are going to call more contracts, and on it goes. And so what a transaction is a proof of correctness of a sequence of function calls, contract calls, that all get recursively composed together via this protocol circuit, I guess you could say, we call the kernel circuit. So the idea is basically, it's almost like a part of an Aztec node. It verifies that a sequence of contract calls have been executed correctly. And so what you get out of that is a zero knowledge proof of a kernel circuit. And then you have a bunch of like public inputs to that proof. Those inputs will describe effectively the encrypted state changes that the user wants to occur, wants to make happen, and also a list of public functions to call. I mentioned before that, you can have private functions that modify this private encrypted state database and public functions that modify the public database. That's so that you can have things like global state that isn't encrypted at all. And the public functions are kind of executed a bit more like a traditional ZK layer 2. So basically, you've got encrypted state changes, public function calls to be made, and a zero knowledge proof that wraps it all together. And that thing is sent to a peer-to-peer transaction network. And so the protocol itself doesn't ensure network layer security. The idea is that you would need to use some kind of mixnet like Tor to get that property. That's kind of V2 of Aztec, you could say, is going to focus more on kind of creating that full end-to-end network layer security. But assuming you've used some kind of secure networking protocol to get your transaction into the Aztec peer-to-peer pool, eventually it's going to get picked up by an Aztec sequencer and incorporated into an Aztec block. And so what happens there is that this is where things look a bit more like a traditional layer 2. You have this concept of a prover that will prove the correctness of a block. So the idea is that you will have a roll-up circuit, and this circuit will verify each user transaction proof is correct. It will then extract from the public inputs the public function calls. It will then construct proofs that they're all being executed correctly. And from that, you're going to basically get a big list of state changes that need to happen. State that needs to be deleted, state that needs to be added. Some of it will be encrypted, some of it won't be encrypted. And so the roll-up circuit is going to be performing all the state updates and also rejecting any transactions that are requesting invalid state updates, for example, double spends, things like that. And then once that's all done, you have a roll-up proof, and that gets kicked out to the Ethereum layer 1 and verified through our Aztec smart contract. And so the idea is that you do basic consistency checks. Is the rollup proof correct? Yes. The Aztec smart contract controls, we call them state roots. So we have this big Aztec database of of everything that is contained in Aztec, and that all gets hashed into a single piece of information, a root that describes what is contained in that database. And so what a rollup proof is going to show is basically going to say, here is the old state root, here's the new state root, and here's a proof that the transition between these two state roots was the result of the correct execution of a block. So you have like 1,000 or so transactions, and each transaction is creating its own state changes, and that all gets incorporated into this new state root. And so the layer 1 smart contract will perform basic consistency checks. So is the old state root actually the state root that is controlled by the contract? And if so, it'll update its state root, its record of what the Aztec layer 2 says to be what gets spat out of the rollup. Anyway, yeah, that's a bit of a lightning tour of how it will work.
It's quite impressive. So you have client-side proving, you produce a proof of that transaction, you have it sent to operators which function in a specific way that ensures, I'm trying to recapitulate it in the simplest way as possible, that nothing gets compromised, then everything is batched, and we get like a proof of a proof, so a recursion of some kind that is then sent to Ethereum for verification. I just aggregated and shortened and trimmed some chapters out, but is that right?
That's it. That's perfect. Yeah, that's what
okay. And correct me if I'm wrong, Zach, but a lot of rollups are just going for down the validity rollup road because you get that succinctness, you get that scaling property, and you're able to cram more stuff in the same object. That implies less computation. Well, if you want to preserve privacy at all costs, like throughout all the process, you want to ensure that privacy is preserved, that implies more computation. So I would like to ask you about the cost logic, a system like Aztec. What goes into the development of the Aztec network to ensure that we'll be able to have that fully private experience while maintaining costs that are reasonable?
It's a good question. So you have, what are the resource costs? You have computational costs for like producing a block, and you also have the cost of data that you're adding to a blockchain network. So let's start with computational cost. Paradoxically, actually, the computational cost isn't as great as a lot of other ZK transparent layer 2s because for transparent layer 2s like Polygon 0 or ZK Sync, you have to prove the correctness of an Ethereum block because they're Ethereum compatible. And simulating the Ethereum virtual machine is quite painful because it's not snark friendly. Whereas because we're designing our architecture from scratch, we can make sure that what we're doing is snark friendly. And so whilst the computational cost is not negligible, compared to the cost of data, it's not something that we're greatly concerned by. It's more that computational cost more influences things like how quickly can you make a block. But in terms of like the actual like machine cost, like for example, to rent these machines from AWS, it's not that great compared to the data. The data is the expensive part because with a encrypted transaction, a privacy preserving one, all your data is encrypted, and that increases its size. So no matter how small your data type is, it's going to blow up to 32 bytes of information when you encrypt it. And then if the intended recipient of a transaction is not the sender, then you need to communicate with the recipient how to decrypt that data, which adds additional data loads. And also, because of the nuances of privacy, if you want to read a private state variable on your blockchain in your program, that also it adds data to your blockchain network, just the act of reading it. Because to prove that you've correctly read a state variable, if you don't do it properly, it will leak some information. What you actually have to do is you have to destroy that state variable and re-encrypt it and add it to the state tree to kind of hide the fact that it's being read. So a typical Aztec transaction will be like a kilobyte of information, whereas like a standard Ethereum transaction is like a couple of hundred bytes at most, I think. So that's the considerable cost. And so the steps we're taking to minimize that cost. Well, on day one, we're going to be using EIP 4844 blobs. So that'll give us some scaling advantages. But longer term, we are likely going to have the ability for users to select a different data availability solution. So instead of using the Ethereum L2 for data availability, we'll use a purpose-built data availability network like Celestia that'll provide strong guarantees, but also enable us to lower the costs for users.
So some kind of volition mechanism. You choose your DA.
Exactly. Yeah.
All right. And because you're dealing with this privacy component again, scaling is a bit harder to achieve to a certain extent, even though everything is designed so that proof generation is optimized and everything is well glued together. Let's put it this way. Do you have an agenda for an L3 stack, an Aztec?
Yes.
Yeah.
Absolutely. So we do focus on scaling as well, because obviously, you need a high throughput to really unchain the blockchain. But a private layer 2 will never be as scalable as a public layer 2, just because the amount of data is larger, which means the cost of your transaction is going to be a small multiple larger than a transparent transaction. So yeah, the Aztec stack, what's that going to look like? I'm a firm believer in this quasi app chain thesis, the idea that right now we're bundling a lot of security properties into a blockchain network where a lot of applications in this world don't need all those properties. So you have censorship resistance, you have permissionlessness, you have strong liveness guarantees. And let's say I'm making a game, right, and I want my game assets to be tradable, and you'd like to interact with some kind of like larger multi-game universe. Well, I don't care about data variability. It's a game. Like game players trust me to run a server that contains all the game state. I don't care about censorship resistance. I probably want to be able to censor my users in some ways, if they violate terms and conditions. What I really want is the composability of a blockchain network, the ability to print these digital assets and allow users to trade them and convert them into other assets. I want to be able to have efficient and convenient on-ramps into that ecosystem. So what we want to do is effectively, much like the OP stack, enable kind of like extremely efficient deployments of Aztec Network. I guess you could call them clones, but ones where you can configure the security properties. So you can say, okay, we're not going to have a decentralized sequencing network. I'm going to be the sequencer. My server is going to be sequencer. We're not going to have a data availability solution. Just my server is going to be the data availability solution. And what happens is that network operates semi-independently, but there's only one application on that network. And at like deterministic checkpoints, that network's they're going to produce rollup blocks that get settled directly within an Aztec layer 2 smart contract. And that way you get strong composability, you get private on and off ramps into that ecosystem, but you also get massive amounts of throughput, because you don't need to worry about block selection. You don't need to worry about data, broadcasting a ton of data over a peer-to-peer messaging network. And I think that that's likely how most applications will be developed on blockchain in the future. If I'm doing micropayments, I don't care about permissionlessness and like the integrity of data. Neither do my users. As long as they only have to trust my network for 24 hours, that's fine if you're sending 10-cent transactions around. Or if I'm doing I'm running I don't know, some kind of community group as a decentralized organization, and we're holding votes and we're organizing meetings and we're deploying resources. As long as like everything that happens within 24 hours gets put on chain, who cares about those ironclad security guarantees? Those ironclad security guarantees are needed for assets, for money. I don't think they're needed for like short-term interactions involving those assets, if that makes any sense. And so yeah, we're very much planning on creating an Aztec L3 stack where the idea is that you're writing your application in Noir, and it looks like you're just writing a regular smart contract. It's just that ideally all that happens is some configuration settings are changed so that when you actually compile and deploy that contract, it gets deployed to a layer 3 network running on a private server instead of directly deployed to Aztec.
All right, so we mentioned like L3 stack, Aztec stack, composability, and I feel like there are a lot of people on Twitter that are telling that real-time settlement proving is okay theoretically. Some folks know how to do it, and that it's just up to engineering and eventually hardware acceleration, snark ASICs, to make it happen. Let's put it this way. This has to mean something, right? What's your take on that as the solution to solve liquidity fragmentation and L2s? As a Snark Goblin, an expert in the topic, I would love to have your input on this.
As a resident Snark Goblin, yeah. I think engineers often fall into this fallacy where if you know how to do something, you assume it's already been done or that it's trivial to do. And this is very much the case for this whole ZK narrative, particularly because it is a narrative, right? It's a very popular narrative to raise a lot of money and build a startup. And there is truth to it. As in, yes, in the future, it will be possible to, in real time, prove the correctness of the state of an L1. So you'll be able to prove in real time Ethereum is correct or Bitcoin is correct or Solana. Well, maybe not Solana. That'll take some more time because it's more complicated. And so the idea there is if you can do that kind of real time proving, then you can have smart contracts on all these layer 1 networks and layer 2 networks that embed light clients of all the other layer 1 and layer 2 networks. And via doing that, you basically trust the swaps between those two networks because you can verify that funds have been deposited into an escrow contract on Solana within an Ethereum smart contract, which can then which can release some funds on Ethereum and vice versa. And that does possibly enable mass composability between layer 1s. I think the devil's in the detail because what was happening there is effectively you're trying to create an interoperability layer between different networking standards, really, which is not easy. In a way, it reminds me of the protocol wars in the 1980s or the 1990s between IPv4 and whatever the hell the competitor to IPv4 was, which I do not remember. And whilst, yes, you could have created an interoperability layer between those two that enables them to coexist, the simplest solution was just for one to die. So I am a little uncertain about whether we're going to have this whole mass composability between like a massive amount of L1s and L2s. I still think that fundamentally every single network needs to justify its own existence through having some unique value proposition. If you're serving the same use case, the same user base with the same product offering, one of those networks is going to die because it's going to get outcompeted by the other. That's my take, at least. So I think it's going to partially come true, this idea of a like mass composable, everything will be interoperable with each other through proving, but it's not going to quite pan out, I think, in the way that some of these more idealistic takes are projecting.
Cool. And finally, I think that the Plonk paper was released in 2019 or 18 with Ariel Gabizon, yourself, and Oana Chebotaru, and it is now one of the most widespread or used. Can I call that a proving scheme? It's not a proving scheme. It's proving scheme. Put it this way. It's finally in production. There's been quite a gap until we see mature system like using it. Yeah. Could you give us a high-level introduction to what is Plonk? What are different components of Plonk? The IOPs, the PCS. Break this down for everyone here. The folding schemes.
Yeah, I can. Yes. So Plonk is a bit of a chimera in that the version of Plonk that we published in 2019 was at the time the fastest SNARK protocol. Nowadays, it's a bit slow. It's actually quite slow and inefficient. Yet people are producing production versions of Plonk systems or Plonkish systems. And why is that? It's because Plonk is more of a framework for designing a SNARK. So back in the day, before 2019, if you had a SNARK cryptography protocol, you would publish it as a monolith. So you'd have this like very complicated algebra and protocol logic that defined how to encode a SNARK circuit and prove it. And it wasn't modular. And so every protocol was unique. Every protocol had no real similarities with any other protocol. And what Plonk did was it was really the first protocol to define abstraction layers that can be used to assemble SNARKs. The idea is that you have the concept of a polynomial commitment scheme and an interactive oracle proof and circuit arithmetization. So circuit arithmetization is how you turn your program into constraints. Basically, what are the constraints? What is the kind of the formula, the algebraic formula that you're going to want to try to prove? Then a polynomial interactive oracle proof it's a protocol to prove that that formula is correct, or at least basically it's taking a complicated formula that applies to extraordinarily large polynomials and it reduces it down to a formula that's applied over single points. And then you use this polynomial commitment scheme to verify that final check. I'm kind of glossing over it because that's a whole 1 hour talk subject to break that down. But the idea is that you have this 3-tier structure where you could modify any of those 3 layers, but still preserve the layers that you're not touching. And that was quite radical. And also what was quite radical was that the actual algebraic formula that your prover and your verifier are checking map directly to the arithmetic of your constraints of the addition and multiplication gates in your circuit, which wasn't a thing before. And so you combine those two properties, and it means that you have an enormous diversity of Plonk-like systems where, for example, very quickly after Plonk came out, I gave a talk where I talked about this concept of custom gates. So you can move beyond having just addition gates and multiplication gates. You can create these gates that are a bit more like instructions in a CPU that perform operations that are more useful in a real world context. And then we as in the community develop more advanced polynomial commitment schemes. We develop more advanced interactive oracle proofs like sum checks. But you can still take all these frameworks and take all these components and plug them into a Plonk style framework to create a proving system which looks a lot like the original Plonk protocol. So yeah, that's kind of, I'm not sure if I answered the question. What was your question again?
That's a high level overview of what is Plonk and how it is, the different components that are implemented on Aztec to make it work. And if you want to learn more about Plonk, there's a website called Cryptology by David Wong, who was our previous guest, that takes you over how Plonk functions at a high level, which I recommend. I've been there before recording this podcast right now, and I definitely do recommend that resource. And you've mentioned folding schemes. I do remember in Stanford stumbling upon a guy called Srinath Sethi talking about hypernova or something like supernova. And the joke back in the days within the ZK community, well, I mean, not the joke, but like the tackle was that folding schemes are going to make all Fry-based proving schemes like out of competition. I reckon that you're using one for Aztec, and it's called Goblin, and it's an accelerator for the whole system. How far can the optimization go?
How far can the optimization go? Honestly, I feel like we've barely scratched the surface. As in, folding schemes are very powerful because they address a difficult problem in the field of snarks, which is this concept of recursion. Basically, the desire to create a snark circuit that verifies a proof of another snark circuit, or that traditionally has been extraordinarily difficult because, at least if you're using elliptic curve-based snarks, effectively what your snark circuit, all your arithmetic statements are going to be over perform modulo some very large prime number. And if you want to verify a proof of knowledge using the same parameters as your circuit, then you have to do a lot of very complicated arithmetic over a very large prime field that's different to the prime that your circuit is natively handling. And that's been a very hard issue. I've spent a lot of time in the past trying to solve this, a lot of time. And folding schemes are a great solution, partial solution, because what they do is they reduce the amount of work that your verifier algorithm needs to perform. Instead of verifying proofs, what you're doing is you're aggregating claims about circuits. So it's almost like you're aggregating partial proofs, and then at some later stage, you construct a single full proof instead of having to construct full proofs for every single circuit. But it doesn't get around this fundamental issue in recursion of having to do this. We call it non-native field arithmetic. And so Goblinplonk is a solution to that. So we combine it with a folding scheme called ProtoGalaxy. And Goblinplonk is a way of basically converting that expensive, painful non-native field arithmetic into native field arithmetic. And we've only scratched the surface, to be honest. Like we have performance targets we want to hit for our V1 of Aztec. And once we hit them, we're going to just focus on security reviews and audits because we want to get this thing released and it needs to be secure and stable. But we could spend another year optimizing it to make it like stupidly fast if that was the priority. It's a very exciting time where these folding schemes are going to change the landscape of what you can do with these kinds of recursive snark constructions.
And what's like pretty impressive when it comes to Aztec is that according to your targets that you've introduced at the previous ZK Summit, not the one in Athens, but in London, I reckon, you're looking at having a bunch of that cryptography running on trivial, basically like domestic hardware. Yeah. So you really want to push the optimization at a level where any average user can just on their boat.
Yeah, for sure. For sure, like the target is like we want to take a medium complexity Ethereum transaction, say like a Uniswap trade, and we want to, when converted into Aztec land, for that to be those proofs to be constructed on a user device in a web browser. So this is you can't even use, you're not running natively on a laptop silicon, you're having to go through a web browser environment and to get that proof done in under a minute, which for V1, it is a long period, it's a long time. We're under no illusions, but we'll improve that over time. We really just want to focus on security soon. But when I started this journey in 2018, that proof would have taken an hour, probably longer. And it would have required about 100 gigabytes of memory, which a laptop does not possess. So, it has been quite a monumental leap in performance, for sure. It would take about 10 hours if you did it in WASM with 2018 tech. It would take about 10 hours, and we're getting it down to a minute. So, yeah, the tech has advanced a lot.
Yeah, I do remember that. So you mentioned Zcash. First prover that was used for it was BCTV14, and it was found later that there was a soundness leak in the system. Yeah. What is the rigor and the approach to audit state-of-the-art cryptography, like these cutting-edge systems, and ensures that the user is actually safe using those? And then once I'll get your answer, I'd love to dive deep on the training wheels and protocol upgradability. But before, I'd love to understand what's the whole flow to formally verify to prove to a certain extent that this
cryptography. For sure. So the BCTV14 bug the Zcash bug was quite unusual actually, in that it was a bug in the actual protocol paper. Normally bugs are found in the implementation side. So you have a cryptography paper and then you put it in code, and it's actually that translation that's the problem. So with regards to how do we secure it? So step one, obviously fully defined protocol specifications that gets reviewed by multiple people, that we pay external auditors to review, we make them open source. Then the next step is, so we have our implementations of software where obviously we're doing very rigorous internal reviews of the code as it's being created. But once we have a kind of a version, like a a V1 specification, then we freeze the code. It undergoes external audits and very thorough internal audits, as well as obviously like a large amount of communication with the community and generous bug bounties. At the moment, that's kind of the current standard, effectively. Like the quality of external auditing firms in the ZK space has increased dramatically from where it used to be. It's still I wouldn't expect anyone to trust an external audit. It's kind of it's nice to know it's past external audit, but generally the way we think about it, it's the internal audits that really matter, and making those thorough is extremely important. We're building a red team within Aztec, whose literally just goal is just to go around and break other people's stuff within the company to see how far they get. But ultimately, it is extremely difficult to secure a protocol, like a complicated ZK protocol, and the one ingredient that's really required is time. You need time where the stuff is in the public domain, is kind of being used, and there's eyeballs on it and people looking at it, where there's incentives for people to find and report bugs because, for example, bug bounties, because it's going to be very beneficial for them to do so. So we are planning on launching our testnet later in this year, where we're going to be rolling out the bug bounty program, and just trying to get as many eyeballs as possible on it before we go into our open alpha phase.
Yeah, quite impressive, and there's a lot of thought that goes into designing also systems that ensure that in case of a security incident, a fast response can be actually adopted without sacrificing.
I completely forgot about going through that, and that is very true. And also, that's something that's been challenging for us, because we're planning on launching this network as a fully decentralized network from day one. So we're not going to have a centralized operator that can just hit a button going, no, sorry, pausing the network, we're fixing a bug. There are many reasons why we want to do it fully decentralized, but we feel like it's quite, given the sensitivity of our technology, it's quite important that people trust that it's not being manipulated or controlled, or that there aren't backdoors, things like that. But we do want to be able to rapidly fix issues as they're reported, and so the plan is to have the upgrade mechanism is going to be fully decentralized. So effectively, what's going to happen is it's going to be through sequences are going to be the ultimate final entities that choose whether to go with an upgrade. So as blocks are being produced for the network, sequences will be basically voting for what version of the network they would like the next blocks to be made from. And once you have a plurality of sequences agreeing to the upgrade, then an upgrade goes through. As for pausing the network, that's going to be through a security council. So a distributed body of a relatively large number of people, where a majority of them are going to need to agree to pause the network. And so something that we're taking very seriously is A, assembling that council, and B, being very rigorous about ensuring that the response times for that Security Council are fast, and doing constant training for it and constant fire drills, because that is going to be absolutely critical to the long-term health of the network, to be able to rapidly kind of pause block production so that we can fix any security issues that are reported to us.
Yeah, and as usual, I'll be leaving some interesting resources in the description if you guys are interested. Joe Andrews has written a post on ways to potentially approach such situations on the Aztec Research Forum. So if you'd like to learn more about that, I'll be including all the relevant links in the description below this YouTube video. And you've covered some design elements of Fernet, but could you just reintroduce this network decentralization framework for those who are not familiar with it, please?
Yeah, Fernet it's a protocol for sequencer selection. So there's a question around, okay, so you need to be able to produce blocks for the Aztec network. Who produces those blocks? How do you select your sequences? We have some unique challenges associated with Aztec that aren't present for other layer 2s because of the privacy angle. Effectively, normally with the ZK layer 2, you have this asynchronous queue where the idea is that block producers construct blocks, they paste them on chain in a queue, and then provers turn up, and they will basically prove blocks that are in the queue. So what that effectively means is that you can produce a block prior to proving it. We don't have that luxury, because in Aztec, a block contains all of the user transactions, and each user transaction contains a zero-knowledge proof that's several kilobytes, probably about 10 kilobytes, which is way too much data to put on chain. However, if the block comes with the proof of correctness of the block, those individual transaction proofs can kind of get swallowed. They can be private inputs to the block proof. And so it means that every block has to basically come with its own proof for now. We're upgrading Fernet to remove that requirement, but for the very, very first deployment of Aztec, that's going to be the case. And so the question is, how do you select these block producers? How do you do it in a decentralized way so that you don't get anybody monopolizing it. And how do you do that without building a fully fleshed consensus network? Because we want to leverage Ethereum as much as we can for consensus. So it's a difficult problem that, oddly enough, hasn't actually been thought about a huge deal before we started thinking about it. So we put out a bunch of requests for proposals to get like public feedback and suggestions. We got an enormous amount of community feedback, a lot of suggestions, and a lot of those ideas made their way into our final protocol, Fernet. But effectively, Fernet it's an auction type system where you have random weights, like a randomly weighted auction, so that the block producers are staking value on the ability to produce blocks. The more you stake, the more likely you are to be selected as a block producer. But the devil is in the detail, and it has been a little bit of time since I've actually been in the weeds of Fernet, so I don't want to give any fake information. But Sam, I don't know if you have the actual design specification. If you could link that in the podcast, that would be extremely helpful.
I'll, of course, be adding them to the resource section, of course. Yeah, I wanted to pick your brain on something else that seems to offer similar properties as what Aztec do offer. It's the FHE, which is getting more and more popular to a certain extent. What's your take on these fully homomorphic encryption solutions that are being built right now?
I think so FHE is super interesting, and I do think that its time will come, but it's going to take a long time. So the thing about FHE, right, is it's partially the holy grail of zero-knowledge cryptography, because it allows somebody to run a computation where they actually have no idea what the information within that computation is. So it means that you can encrypt a bunch of state. It basically means you can have an Ethereum node run an Ethereum program, but all the information, the data in the program is encrypted. That's quite unique. The difference between FHE and ZK, the kind of ZK we use, is that in ZK, you can only make a proof over encrypted data if you know what that encrypted, if the prover knows what the secret information is. Whereas with FHE, the prover effectively can be somebody who doesn't know what the secret information is. So on the surface, it sounds really compelling, right? But there are two problems with it. One of them is that information still needs to be encrypted, which means who holds the decryption keys? If you want to encrypt Uniswap, for example, so you have all these variables about your total liquidity supplies, who encrypts that? Because that's a huge amount of there's a huge trust factor, and so you need very advanced multi-party computations protocols to ensure that encrypted data is not visible by anybody. But if you have very advanced multi-party computation protocols, you could use those with regular ZK to kind of get effectively the same effect. So I'm a little skeptical of that, to be honest. But my main concern about FHE and why we're not using it is the extraordinary computational costs of FHE. So to run an FHE computation in any kind of meaningful time, you don't just need GPUs. You need custom silicon. You need to etch directly into silicon FHE algorithms to make them remotely fast enough. And that means that if you make a blockchain that's FHE based, your blockchain nodes need to possess this custom silicon, which dramatically limits the number of network operators and makes it difficult for it to be permissionless and decentralized. The solution to that problem is what you really want to do is you want to combine the two technologies. You want to create zero-knowledge proofs that prove that FHE computations have been performed correctly. Because then what you can do is you can have one or two provers who are massively well resourced. They have a huge amount of this custom FHE silicon, and they're running these FHE computations and proving them. And then you have very computationally weak network nodes that just verify these proofs. That would be the holy grail. But the problem there is that the difficulty of proving, running an FHE computation natively is extraordinarily expensive, and you need custom silicon for that. To then make a zero-knowledge proof of that, you're adding an overhead of at least 100,000. So with the state-of-the-art technology the way it is today, I don't see it being practical or possible. I think it will become possible. It's going to take many, many years of people grinding at the bleeding edge of technology, kind of the way what I was doing from 2018 onwards. So I do think it's going to happen, but that's the next generation's challenge. I want to productionize privacy tech today, which means FHE is not it right now.
I would say it's at its Plonk paper stage right now.
Yeah,
there's a gap until it actually becomes
there's a big gap.
Useful by real mortals.
Yeah, but its time will come eventually.
Oh, that's super exciting. Out of curiosity, I was wondering if you ever had a chance to do some Noir quest on Node Guardian, Zach.
I did one Noir quest when I was acting as a beta tester. But I must confess, I have been meaning to do a lot more, and I'm getting it's one of those things where it's I know how to program Noir, so I don't need to do Noir tutorials. But I mean, honestly, I was trying out what you guys have built, and it is the level of polish and the production values is absolutely insane. It's best in class, and there isn't anything close. It really blew my mind. It really blew my mind.
Truly humbled by your words, and we do hope to broaden the scope of what we can offer on the platform as well. But for anyone that's interested in Noir, you are more than welcome to check out the documentation that's provided by Aztec, but also Node Guardians, where we have a few challenges that will help you to become more familiar with this new language and what it enables you to do. That's something that I'll also link in the description. That's pretty much it. Do you have some extra remarks or information you'd like to share with us, Zac?
Any extra remarks? So if you want to learn Noir, noirlang.org, Node Guardians is the best place. If you want to learn more about Aztec, go to Aztec.network, join our community. We have a very active discussion around a lot of our technical details and protocol design details in our forums. So feel free to join the discussion. And thanks for listening.
All right. Yeah, thanks for being with us, Zac. It was truly a pleasure to have you. And thanks to everyone who tuned in, even though this wasn't meant to be a stream. We've had a lot of fun, and I will be uploading this episode on the Node Guarantee channel. Thanks again, Zac. It's good to have you.
Thanks.